Okay, so this is for a third period because we did not get a chance to finish this worksheet. So we were discussing that there is a shortcut for finding the area underneath a curve rather than making the Riemann sums where you had to take the rectangles and figure out their areas and add them all together. Instead, we said that you can take the sum of all the rectangles that have a height and a width that you get from using the equation of the line that you graphed. So on this particular equation, our graph was y equals x. So I can say f of x is equal to x. So I'm going to take the sum of all the rectangles that have a height of x and a width of dx, because dx can be whatever we've decided to break this up into. So if I do that, I'm taking the antiderivative. So the antiderivative of x would be 1/2 x squared. Because remember our rule, we add 1 to the exponent, and then we multiply by 1 over this number. So that's the antiderivative of x. It's 1/2 x squared. Now we have to evaluate it for the x values from 1 to 4. And the way we do that is we put on here, this is the notation, we're going to start at 1, we're going to end at 4. The way that we do that is we figure out, well, what's the area at the end when x is 4? So 1/2 4 squared, and we subtract off the area at the beginning. So 1/2 1 squared. And then we simplify that. 4 squared is 16. Half of 16 is 8. And then 1 squared is 1. Half of 1 is 1/2. 8 minus 1/2 is 7.5, which is the estimate that we got when we did it in class. Or not even an estimate, when we actually figured out the area of this region right here. We were able to completely get that area by using our knowledge of triangles to get 7.5, and now we've done it using an integral. All right, so the area under the curve. So this curve is y equals x squared. So f of x is equal to x squared. So I want the sum of all the rectangles that have a height of x squared and a width of dx. And dx is whatever width I've decided to make those rectangles, right? We want them to be as small as possible to give the best area. And we're going to evaluate this from 1 to 4. That's how we write the notation. So now I'm going to take the antiderivative of x squared. The antiderivative of x squared is going to be x cubed times 1 over that exponent, 1/3. And I'm going to evaluate it from 1 to 4. So when I write that out, I have 1/3 4 cubed minus 1/3 1 cubed. Then if I multiply that out, 4 cubed is 64 times 1/3 minus 1 cubed is 1 times 1/3 is 1/3. I'm going to go ahead and multiply 1/3 times 64. That's just 64 over 3. Keep my minus 1/3. Notice they have a common denominator. 64 minus 1 is 63. Divide by that by 3, and I get 21. So whoever estimated 21, when we did that in class, way to go. That is exactly what the area is. By using our antiderivative, we can find the exact area underneath a curve. Okay, so 21 units squared. All right, so on the last page, so notice I kind of wrote this out. The area under a curve can be written as a sum of all the rectangles under the curve, where the height of each rectangle is f of x. That's how we got the height of each of our rectangles, was by using the equation of the curve. And the width of each rectangle is the change in x, or delta x, which we write as dx. So this can be written in summation notation. So we're adding together all the rectangles that have a height times a width, and x equals n, so starting from wherever it is we are on the x-axis to wherever we want to stop on the x-axis. Okay, and so our height, another way of writing that, is f of x, and our width, another way of writing that, is the change in x, the dx. What does that remind us of? The integral f of x dx. Okay, so it reminds us of this, our antiderivative that we've been working with. And the only additional thing that we haven't seen yet is these numbers for x. So that's just telling us what numbers are we going to plug in for x. So whatever our starting number is and whatever our ending number is. And that's how we write the notation. Okay, so that's finishing up the classwork, and now we are going to do notes. So I'm going to stop this video and start another video that is what is going to go into our notebook.